Actually, it's a much more general introduction to the basics of scattering amplitudes. And I'm actually hoping that for some people, this is more a review than an introduction, but I'm assuming that there are some people for whom it really is an introduction. So we're going to look at the basics of scattering amplitudes and all the, at least a taste of the new on-shell techniques that have been developed in the last 2 to 3 decades. And these techniques have come with a new subfield of high-energy physics, which is called quantum scattering amplitudes, or just amplitudes. And in this area, it's the amplitudes rather than the quantum fields that are the central objects of study. And if I might quote my longtime collaborator, Lance Dixon, it's a way of doing quantum field theory without the quantum fields. So let me actually start by asking how many people here have had a quantum field theory course? Good, that's what I was expected. So this is an area which now has had annual conferences for, about 15 years, and there are now about 200 or so people attending, up from about 100, let's say, a decade ago. And it's a very young crowd, so if you attend one of these things, you'll fit right in. And there's also a kind of sibling conference, which is called QCD Meets Gravity, and that will be held here next week. How many people are planning to attend that? Also good. So, so people are interested in a wide variety of subjects, and that includes things like solving n=4 SUSY, studying n=8 supergravity, studying more generally the analytic structure of perturbative quantum field theory, the mathematics of polylogs, elliptic functions, and beyond. Also, there are some people who are interested in finding new principles to reformulate quantum field theory. And as I've already just said, studying amplitudes is kind of a first step in that direction, and that's removing the quantum fields from the central role they have played, let's say, in the last 50 years. Finally, there's QCD for particle colliders. And more recently, computing observables. Unfortunately, with this chalk, I know my handwriting is anyway not the most pristine. For, I think I'm just not going to be able to write this low. For classical gravitational waves. So traditionally, these subjects would all be addressed using Feynman diagrams, or perhaps general relativity for gravitational waves. which everyone of you has learned in your quantum field theory courses. And that's linked to the fact that the viewpoint for quantum field theory today that everyone here has grown up with is that of path integrals. And so Feynman diagrams are the way to do operator product expansions for a path integral. Now, most of the frontier subjects here can't actually be done that way because there's a factorial growth in the number of diagrams as both the number of loops and the number of legs, or as the number of fields in the theory grows. And that means that there's an enormous complexity of intermediate expressions. And of course, the factorial growth can even outrun the exponential improvements in computing power that come with Moore's law. So you can't just throw more computational resources at these problems. And in many of the frontier areas, they've been superseded by so-called on-shell techniques. And that's what we're going to focus on understanding in my course this week. So what are kind of some of the key ideas here? So first of all, you use information only from physical states. And we'll see very concretely at tree level and loop level what that means tomorrow and on Wednesday and Thursday. So the trees and the loops still contain off-shell states, unphysical states. But we don't use them directly. The other key idea is the use of properties, of general properties of scattering amplitudes and turn them as tools for computing. So there are three key ideas here. First of all, that is of factorization. And if you've forgotten what you've learned in your QFT course, don't worry. I will review that. So this gives us what are known as the on-shell or BCFW recursion relations. For tree amplitudes. And also for rational terms more generally. We have unitarity, that is the conservation of probability, which gives us the generalized unitarity method for loop amplitudes. Finally, the fact that we have a path integral gives us a representation in terms of Feynman integrals. And they play a key role. In fact, it's some of the kind of frontier research is still devoted to understanding how to better manipulate and simplify Feynman integrals. So we have to be very clear about the distinction here between the Feynman integrals and Feynman diagrams. So the Feynman integrals will continue to play a very key role, even though we're going to relegate Feynman diagrams at most to a role in Gedanken calculations. So let me mention a few references. So there's the book by Henrietta Elvang and Yutin Huang, which I suppose for the sake of their royalties you should actually buy, but it's also available on the archive. And there's a book from Johannes Henn and Jan Plewka. I think there may actually be, if it's not out, there may be a new version upcoming. There are lecture notes by Vittorio Del Duca, which I don't have the archive reference. And finally, there's some elements in Tony Z's QFT textbook. The second edition, and I don't know if there's a following edition or not. So one of the questions that, of course, is a natural one to ask is why should we expect there to be any better techniques than Feynman diagrams? And so if we look at Yang-Mills theories, for example, and these are the ones that are of the greatest practical importance in collider physics, and general relativity can be cast in very similar kind of terms. That's what's relevant for gravitational waves. Then, as I mentioned, we have this factorial proliferation of intermediate expressions, but the final answers that we often find are much, much simpler, and they don't grow factorially, not even close. And a celebrated example is that of the Park-Taylor amplitude. How many people have seen it before? Okay, so for some people it's a review, and for other people it's not. So this is the color-ordered amplitude for an MHV configuration, maximally helicity violating configuration of gluons. So we have most of the gluons of positive helicity. And 2 gluons of negative helicity. And we can write down a one-line formula for an arbitrary multiplicity, for an arbitrary number of external gluons. And so this one-line formula summarizes the result of doing an infinite number of Feynman diagrams. And that happens because actually most of what you're doing when you're computing Feynman diagrams is gauge junk. It's stuff that is gauge dependent and is going to cancel out at the end of the calculation. And this is a particularly good example of how simple the result can be when you squeeze out all of that. So, by the way, I'm throwing in bits of jargon here as I'm going along, and don't worry, for those of you who haven't seen it before, the jargon will be explained as we go on. There's another kind of interesting historical anecdote about this expression, which that in spite of the fact that it's called the Park-Taylor amplitude, it was not written down by Park and Taylor. It was written down shortly thereafter by Mangano, Park, and Zhan Shu, who was at Tsinghua University at the time. And it's maybe an interesting example of how people don't always get the attribution of things they do. So if we believe that simple results should have a simple calculation behind them, that's a line which I've heard attributed to Feynman himself, then we should have a simple way of deriving this and ideally squeezing out all of the intermediate complexity that would arise if you tried to do this by Feynman diagrams. So Park and Taylor themselves did not make use of the new tools. History doesn't work in a simple way. In fact, it was the simplicity of this result that led people to understand that there could be simpler tools. They did this by various tricks and then a bit of guesswork. So the first thing you'll observe, and then again, many of you already know what it is, there's this funny looking angle bracket here, which is something called a spinor product. And it's, in a certain sense, a square root of a Lorentz invariant. And the use of spinor quantities and spinor variables is actually critical to the simplicity of on-shell results. So our first task is to learn about them. So we're first going to learn, or for some of you, review kinematics. So we're focusing on scattering amplitudes, which I'm going to generally represent by pictures of this sort. And they involve various external momenta, which I'm going to label by I, or just Ki, so K1 through Kn, or just the indices for simplicity. And by convention, the momenta are always taken to be directed outwards. Now, in general, of course, these momenta will be massive, but in a certain sense, the most important case is the massless case, and it's also the case with the highest symmetry. And so it's the best starting point for studying simplicity. We will come back to look at the massive case most likely on Friday. So we know that we're trying to get, or at least thanks to what you've seen on the board, we know that we're trying to get to a square root of a Lorentz invariant. And so our first task is to learn how to take the square root of a Lorentz 4-vector. And we're going to do that by introducing the 4-vector of Pauli matrices, which is just the identity along with the 3 Pauli matrices that you know well from undergraduate quantum mechanics courses. I'll write them out anyway. So the indices here, there's 2, and by convention, they take the values 1 and 2. And we can use them to rewrite the 4 momenta as 2 by 2 matrices just by dotting the momentum into this 4-vector. So I'm going to try to remember to underline the cases where there are matrices, but from the indices, it should be obvious from context whether I mean a 4-vector in its normal form or written in as a 2 by 2 matrix. So we can write this out explicitly in terms of components. So the first thing that we can observe is that there's a relation between k squared and the determinant of this matrix. The other thing we can observe is that Lorentz transformations on the 4-vector turn into matrix conjugation. So if we have some Lorentz transformation lambda, then that corresponds to conjugating the matrix by a 2 by 2 transformation. So these U's are elements of SL2C. So they're 2 by 2 general complex matrices with unit determinant. Now, for massless particles, which is what we want to start with, then the determinant vanishes. And that means that the matrix has rank 1 or potentially rank 0. And that in turn means that we can write it as the outer product of two vectors. So the alpha and alpha dot, which you're seeing both on the left and right-hand side of the equations, those are SL2C indices, and by convention, the spinors come with undotted and the tilde spinors come with dotted indices, but that's just a convention. So these objects are transform as spinorial representations of the rotation group, but you have to be very careful. They're still bosonic. They are not Grassmann objects. How many people here know what a Grassmann variable is? Ah, okay, so you had a good quantum field theory course. So these are bosonic objects, even though they transform under a spinorial representation. So physical states transform under representations of the Lorentz group. And so they're labeled by momenta. And for different spin, then we also need another quantum number to label them. We want something that commutes with the momentum. And so that's provided by the little group. Those are the transformations that leave the momentum invariant. And for massless particles, that's a U1. And it corresponds to the helicity. So in the massless case, then we have a momentum and a helicity, or equivalently, given that we've written it in this form, we have a pair, lambda and lambda tilde, and then along with the helicity. So that labels our states. And there has to be an action of the little group on lambda and lambda tilde. On k, of course, it has to leave it invariant, but that doesn't have to be true. And indeed, it isn't true for lambda. So these things have, as befits something with a spinorial character, it has, in fact, helicity plus or minus 1/2. So we can think of these things as carrying helicity plus or minus 1/2, and this will be important when we construct amplitudes later. So the natural thing is to now form invariant quantities in the same way that we form Lorentz invariants by contracting the vector index. These objects have SL2C indices, so we need to contract them using an SL2C invariant tensor, which is the epsilon tensor. So it's a two-dimensional epsilon tensor. And there's essentially two of them corresponding to the dotted and undotted indices. The important thing to remember is that it does not make sense to contract a dotted with an undotted index. That's why we keep the two indices distinguished. So we get these invariants. And these are, in fact, the spinor products. There's a trace formula so the matrices, like the K and sigma, they do carry one each of each of the indices. And so we would need both of the epsilons in order to contract them. So there's a trace formula that says that we can get a, actually I should write this as eta mu nu, which is just the Minkowski tensor. Let me go over here. So it's convenient to introduce some additional notation. So we can label the spinors just by the index into the set of external momenta. And in fact, it's easiest just to have a notation that drops the tracking of the helicity inside the bras or the kets. And then we need to use an angle or bracket notation. And similarly, we have the angle bra and the bracket bra. And so in this notation, there are two spinor products, ij, angle ij, which we can write out more fully in these other two forms. And so it helps us clean up the notation, which if we're manipulating things by hand or even reading what a computer is spitting out just becomes much more convenient. So this is the first place where I need to warn people about a slight unfortunate bifurcation in the historical record. So the conventions on the angle product are essentially uniform throughout the literature, but the conventions on the bracket product aren't. And the QCD literature has one convention, which is the one that I'm going to follow, and some of the supersymmetry literature has the opposite convention, so where the two arguments are interchanged, and so you have to watch out for that. These objects are the square roots of the Minkowski product, and they're more precisely the square roots precisely in that their product is the Minkowski invariant. And again, in the supersymmetric convention, here it would be ij. So there's a relative sign, and you just have to keep out for that. Now, we can give an explicit representation for lambda and lambda tilde. So if we define k plus and minus to be upper indices, k plus, then, and we define what is supposed to be a phase this way, so this representation implicitly uses the z-axis as a reference axis, but of course that's arbitrary. You could do this. You could choose many other forms, and in fact, there are many other representations that have been used over the years for the spinor product. So this actually brings me to the first exercise. So I will not be solving these exercises for you. Possibly I will, if I'm attending these discussion sessions, I will pick a volunteer and have them go up to the board and solve the exercises. The first exercise is to show that well, I thought this was Nathan's standard operating procedure. So the exercise, so show that e to the I phi is indeed a phase. Okay, so with the help of these quantities, we can write down a representation for these complex 2 vectors. And that means that we can then also write down explicit formulae for the spinor product. So we would get something like e to the I phi j times ki plus kj minus, and then subtract the phase with the other combination. And there's a similar formula, which I won't write down explicitly for the bracket product. And in fact, rather than squaring expressions analytically and re-expressing everything in terms of Lorentz invariance and Levi-Civita tensors, one should evaluate things numerically using spinor products, and then you might use formulas of this sort, and then you'd square an expression numerically. It's going to be typically much more efficient. There'll be an exercise that will lead you through that later. On the other hand, usually you treat lambda and lambda tilde as independent variables rather than using these explicit representations. But it's always good to know that in the same way that k mu could have numerical components, these things also could have numerical components. They're very concrete objects. So if the energies are positive, then in fact the 2 and the momenta, then the 2 spinor products are in fact just complex conjugates of each other, or more generally, we have to adjust for the sign of the energy components. So let's look at some of the properties of the spinor product. So they're antisymmetric, which of course should have been obvious from their definition using the two-dimensional antisymmetric tensor. So, and that's of course also true for the bracket product. And in particular, that means that the spinor product of a spinor with itself is of course 0. So we can reconstruct momenta by contracting with the Pauli matrices, so that, for example, we have 2kj would be equal to sigma mu alpha alpha dot lambda alpha lambda dot. And in terms of notation, this is maybe a less common notation, but I like to write it in this form, or even just with the mu index for short. And long ago, you could actually publish a paper with this one identity. This thing, I don't know if people still bother to mention it in QED, but this thing is known as the Gordon identity. I don't know if it's the same Gordon as the Klein-Gordon or not. Probably. There's also a Fierz identity, and this is one of the two identities that's actually very useful in explicit computations. So if we have two vectors built out of spinors, not necessarily the same spinor on either side, because these two might not correspond to the same spinor. In that case, it's not reconstructing momentum, it's constructing some other vector. If we have two of these and we need to, and we contract the Lorentz index, then we can write it in terms just of spinor products. So, and there's one more identity, which is very helpful. And to derive it, then we can understand that any 2D vector can be written as a sum of two basis vectors. So let's say we have some spinor corresponding to momentum q, then, and we have two spinors that we're choosing as basis spinors, let's say lambda and j. So we know that this equation is going to hold just by the fact that we're in 2 dimensions. And of course, all of these objects are complex. So does anyone see how we can turn this into an identity for spinor products? Okay, no one's volunteering. All right. I won't make anyone come up to the board and do it. So we contract respectively with lambda I. So if we contract there, then I'm leaving the alpha indices implicit here. And of course, this term will vanish. We'll be left with that term alone. And so we can solve for Cj. And if we contract with lambda j, then we can isolate Ci. So then we get ratios of spinor products for these two coefficients. So the angle product of IQ over the angle product of IJ. And if we now wanted to get, so these are ratios of spinor products, and we have one spinor index left, we can contract with another arbitrary spinor, let's call it lambda r. And that gives us what's known as the Schouten identity. So it's an identity, a rearrangement identity for two spinor products oops. And let me give you a mnemonic for keeping track of it. So we're going to go, the first term, we're going to go from the beginning all the way to the end and come back on the inner indices. And that's going to give us the first term here. And of course, the thing that's really critical is to keep track of the sign of the arrows, because if you get that messed up, then you have a sign wrong. And the second term, I hope this is still visible to the audience and the camera, we go from the first to the first and from the second to the second index. So now let's do another suggested exercise to kind of get you to understand concretely the advantages of spinor expressions. So we're going to compute a trace of 6 massless momenta. And so first, you're going to do it the textbook way, using scalar products. Then, using spinor products. And then you're going to count the number of operations for each of these approaches. And finally, analyze how that changes, how the number of operations changes when there are additional momenta. So instead of 6, maybe you're doing 8 or 10. So when we have real momenta, then this is essentially the same equation that I wrote down earlier, there's a relation between lambda and lambda tilde. And the lambda, of course, is not unique because we can redefine lambda by some complex parameter. And because of this relation for real momenta, then that's going to send k to the absolute value of tau squared times k. So we're allowed to make these redefinitions as long as tau is a pure phase. Now, nothing in any of the constructions that we've done, in particular in the structure of the relation between k and lambda, or in constructing the spinor products, actually depends on k being real. The lambdas and lambda tildes are anyway complex. So we can relax that connection, and we get complex momenta which are light-like. And this is actually a very critical ingredient in both the tree level and loop level technologies. So again, as I mentioned before, lambda has weight minus a half and lambda tilde plus a half. We can define a helicity operator, which is basically in a given expression going to, in a given product, just going to sum over the number of lambda minus the number of lambda tilde spinors. And we can express that a little bit more formally by, so we want to sum over all the particles, and we can differentiate with respect to the spinors. So again, you should be thinking of the spinors, lambdas and lambda tildes, as variables, just in the same way you'd think of momenta or position variables. So that's the formal definition, but of course you can just count. And with these, the spinor products and a review of kinematics complete, now we can move on to calculating our first amplitude. So we're going to start by computing the simplest amplitude in Yang-Mills. So this is spin 1 amplitudes. And of course, just like photons, gluons have two physical degrees of freedom, and it's convenient to work, as would be suggested by the fact of having specific helicity properties for the spinors. It's convenient to work in terms of circular polarizations or helicities. So the simplest amplitude we can imagine is a 3-point amplitude. So we have 3 external momenta, and we have, these are all massless, so we pick, for example, leg 3, then we have k3 squared is 0, and we can, using momentum conservation, we can write that in terms of k1 and k2, and we can expand that. K1 squared and k2 squared, again, of course, vanish. So that tells us that that invariant vanishes. And then, of course, by cyclic symmetry, it's true for all the invariants. So actually, all the invariants vanish. And at first glance, that would mean that all the spinor products vanish as well. And so any available quantity that we have with the dimensions of energy vanishes. So the 3-point amplitude has the dimensions of energy. And the coupling is dimensionless. So that would suggest that the amplitude is 0. Now, I didn't actually say this, but in fact, the 3-point amplitude is the basic building block out of which we are going to be able to build every other amplitude, both at tree level and at loop level. So that doesn't seem like a very promising start. And this answer is actually correct for real momenta, because a gluon cannot split into 2 gluons. And the way out of this conundrum is precisely the point I just made, namely we should take lambda tilde that is not related to the complex conjugate of lambda star, that lambda. So in other words, if we do that, then we have to take the external momenta to be complex. And that frees up frees up our degrees of freedom, because the fact that, let's say, angle 1, 2 vanishes no longer implies that bracket 1, 2 vanishes, and similarly for the other products. We still have that the invariants are 0, but now all it implies is that, let's say, the angle products vanish or the bracket products vanish, not both, since they're no longer linked by complex conjugation. So let's start by trying to satisfy the on-shell conditions just by taking the second set, so where the bracket products vanish. And that's, of course, what does that actually mean in terms of the spinors? So the product of, let's say, lambda tilde 1 and lambda tilde 2 is equal to 0. And that is the same thing as saying that the two are collinear, the two are proportional to each other. It's the same as what would happen if you had 2 massless momenta whose Lorentz product vanishes. That means these 2 momenta are collinear. They're going to be proportional to each other. So this is the solution where lambda 1 is proportional to lambda 2. Lambda tilde 1 is proportional to lambda tilde 2 is proportional to lambda tilde 3. So we now have 3 invariants we can play with: angle 1, 2, angle 2, 3, and angle 3, 1. And we can write down an ansatz for A3. So this ansatz has to be a product because, or at least it, so there's going to be some constant times 1, 2, to one exponent, to 3 to another exponent, and 3, 1 to a third exponent. We can't take things like a sum of 1, 2, and 2, 3, because then if we count the helicity weight, or what's otherwise also called the spinor weight, if we do a transformation, the two terms won't transform in the same way, and we'll get something that just doesn't make any sense. So all expressions have to have all terms in an expression have to have a uniform spinor weight, and in the 3-point case, it's only possible for a single term. So now we can do the helicity counting. So we have, for example, 2 appears here and appears here with different exponents. So the helicity with respect to spinor 1 is going to be given by, actually let me call this E12, E23, and E31. So it's E12 plus E31. H2 similarly is going to be minus 1/2 of E12 plus E23. And H3 is going to be minus 1/2 E23 plus E31. So the first thing that we know, I mean, these helicities have to correspond to the helicities of the external particles, so they have to be plus or minus 1. But we have 3 linear equations and 3 unknowns, so, and we want to know what are the exponents E, so we can solve them, and we just get H3 minus H2 minus H1. E23 is H1 minus H2 minus H3, and E31 is going to be H2 minus H1 minus H3. So for example, if we have a 3-gluon amplitude with helicities minus, minus, and plus, we can plug that in, and we get E12 is equal to 3, and E23 and E31 are both minus 1. So our amplitude is going to be some constant times the angle 1, 2 cubed, and in the denominator we have angle 2, 3, angle 3, 1. And if this reminds you of something, it should, because it's exactly the n equals 3 case of the Park-Taylor amplitude. Now, the Lorentz invariant has energy dimension 2. It's a product of 2 spinor products, so each spinor product has energy dimension 1. So this thing overall, this spinor product ratio has energy dimension 1, so the constant is going to be dimensionless. And that's exactly what we want, because that means the constant is going to be proportional to the coupling, because the coupling is also dimensionless. No, 1. Yes, because it's the square root of a Lorentz invariant which has energy dimension 2. Okay, so the first place in which gravity appears is that we can look at the same configuration in gravitational theory. And here, the only difference is that the helicities are going to be plus or minus 2 for the gravitons instead of plus or minus 1 for the gluons. But that just multiplies each of these solutions by 2. So following conventions, I'll use m for the gravitational amplitudes. So this thing is going to be a constant times the angle 1, 2 to the 6th divided by angle 2, 3 squared, angle 3, 1 squared. So if we drop the constant prefactors, so the other thing we can observe, of course, the amplitude itself still has to have energy dimension 1. This thing now is 6 minus 4, so it's 2. So it means our constant is going to have energy dimensions of 1 over m. So if we drop these constants, then you can see there's an amazing relation between these two expressions. And in fact, if I denote the dropping of the constant just by a hat, then we see that literally we have the gravitational amplitude is the square of the Yang-Mills one. And this is kind of the simplest example of the idea that gravity is Yang-Mills squared. And that is something which Henrik is going to discuss at much, much greater length than I will. So here, I mean, in general, this identity is not literally true, but in the 4-point case, it is literally true. And there's a more complicated structure, but this does extend to much more general amplitudes. And in fact, it's a nice point of contact between quantum field theory and string theory, because the very first place this idea was discovered was actually in perturbative string theory, where it's known as the Kawai-Llewellyn-Tai relation that relates closed string amplitudes, which are the string theory equivalent of M3, of gravitational amplitudes, to open string amplitudes, which are the string theory equivalent of Yang-Mills amplitudes. Okay, what about other helicity amplitudes? So if we just blindly move forward and think about plus, plus, minus, then we would get, we just plug them into those equations there, then we would get, of course, the opposite sign solution. And if we just followed that blindly, then we would get something like this. And this, of course, is nonsense, because it has the wrong dimensions, unless the constant were dimensionful, and there's no dimensionful constant in pure Yang-Mills theory. And the other thing that's even wronger about it is that if we do go back to real momenta, then it's not exactly clear how you should interpret this, because it's kind of a 0 over 0, but in fact, these spinor products all scale in the same way as you approach real momenta, and so you can see that this thing is going to scale as 1 over z, or maybe I should call this 1 over e, as e goes to 0, and that is going to be a divergent answer, which is clearly nonsense. So that's not the right way to go about it, but of course, we can see that that helicity amplitude is just the conjugate of the one we just discussed. And so we should use the conjugate variables. So instead of starting with all the bracket products being 0, we should start with all the angle products being 0. Instead of starting with all the tilde spinors being proportional, we should start with all the ordinary spinors being proportional. And when we do that, the analysis is very similar to what we did earlier. We get a much more sensible result. And I should emphasize that the constant here can be different. In particular, it can differ by a sign. So now we get the conjugate of the Park-Taylor formula written in terms of bracket products instead of angle products. And that version of the Park-Taylor formula is known as the MHV bar amplitude for conjugation. And of course, one can do cyclic permutations of minus, minus, plus, or plus, plus, minus. And then we get the corresponding cyclically permuted amplitudes. Again, they're just going to be either the n equals 3 case of the Park-Taylor or the MHV bar, I suppose you could call it the Park-Taylor bar amplitude, although no one does. So there's, of course, 2 possible choices for the helicity of each gluon. And we have 2 times 3, so that's 6 of them. So there's 2 left, which are the amplitudes where all of the gluons have the same helicity. And if we follow the same logic, then we would find that we now have some constant, in principle a different constant, but now it has to be multiplying the product of the 3 different spinor products, 1, 2, 2, 3, and 3, 1. And so the only way for this to be consistent in pure Yang-Mills is for this constant to vanish, because this constant would have to be dimensionful. There is no such available dimension constant. And this is actually a special case of the vanishing of either all minus or all plus amplitudes, which you can understand as a consequence of supersymmetry, or you can also derive it, and after tomorrow's lecture, it'll be one of the things that you will do. So this particular amplitude can appear if there's some suitable higher dimension operator in the theory, and in the case of Yang-Mills, that would turn out to be something like trace G, capital G cubed, where G is the usual commutator of covariant derivatives. It's the field strength tensor for the gluons. Now, I don't know if Henrik is going to devote any time to it, but I'm not going to discuss higher dimension operators in this series of lectures. But it's worth noting that, of course, there's a very rich literature on effective field theories. How many people have seen effective field theories in their courses? Okay, so a handful of people. And you can classify them and then work out the new Feynman rules, work out, typically the things you're interested in are the flow equations for their coefficients. But you can also classify those operators. Instead of approaching it from an operator point of view, you can approach it from an amplitude point of view. So you say, okay, now I have some new interactions in the theory, and those correspond to new amplitudes which would be absent in pure Yang-Mills being present. And that's actually something where there's been a lot of activity in recent years, and some aspects of that are still ongoing. This is more as applied to the extensions of the standard model, so the things like the standard model effective field theory. So, yeah. So whether no, that I don't think will give rise to this. There are analogs of this in gravity, but it's going to be more like some Riemann cubed object. I don't know exactly what it is, and I don't know if Henrik offhand knows exactly the operator that you need to get this thing. No, no. Right, right. But nonetheless, I mean, it's a good question. So if you wanted to ask not with Yang-Mills, but with gravity, is there some higher dimension operator that will give rise to this amplitude in, so of course here it would then be squared, but, and the answer is yes, and I don't know offhand what the answer is. I think it's probably Riemann cubed with some appropriate contractions of indices. I could give it as an exercise, but I think it might be a little bit challenging for people at this stage. Maybe I could give it as an exercise for you to do during the discussion session. But so the one more thing that we need to, yeah, I'm running a little bit behind because I'll blame it on the chalk. So the question is, what is the constants that we've been seeing here in that amplitude? So if we look at this expression, then of course we know that the gluons are bosons, so an amplitude should be symmetric in the exchange. But these two spinor products just exchange between each other if you exchange, let's say, 1 and 2, and this thing clearly has a minus sign cubed, so there's a minus sign. So the constant is not quite right. The constant cannot be symmetric in the exchange. So the constant, in fact, has to carry indices. So it has to be anti-symmetric when you exchange the two indices. And that means that it actually should be, it has to be anti-symmetric. So that means it has to correspond to a Lie algebra structure constant. And that is how the color degrees of freedom show up. So we have an FABC, and we'll talk more about the color structure at the beginning of tomorrow's lecture. And so the object we've written here will become a full amplitude once we multiply with these FABC, with an FABC. And so the object with just the coupling, or even the coupling removed as well, is called a color-ordered amplitude. And maybe in less politically correct language, be called a color-stripped amplitude. In gravity, we've already seen that the constant has to be dimensionful. On the other hand, there's no issue with Bose symmetry, because if we exchange 1 and 2, okay, these two guys exchange it between, and this thing just gives a +1, which is the correct statistics for the graviton. And so here it's vanilla. It doesn't carry indices, and that's a good thing, because there wouldn't be any indices in gravity for it to carry. And it turns out that this mass scale is up to various factors of 2 and pi, which you can look up, is just going to be the Planck scale. So in other words, the coupling here is just up to factors of 2 and pi, is just going to be the square root of Newton's constant. Okay, so I guess we have time to do one more thing. So here we actually derived kind of the basic building block without ever looking at a Feynman vertex or a Feynman rule, but it's maybe helpful to understand how it's connected to the Feynman rules. So if we look at a textbook, and there might be some slight variation between textbooks, and we strip off the FABC, then the three-point vertex will have the following form. I've gone ahead. Usually the vertices are given with indices, right? So there will be some momenta with an index, and there will be some eta mu nu. I've contracted these into polarization vectors for the external legs. But otherwise, this is just the same thing. And of course, there have to be the cyclic permutations of that same first term. So the normalization here also depends on the normalization of the coupling and the FABCs, the normalization of the FABCs. So, but anyway, there's a constant there, which, in fact, in this approach is just G times FABC. Here, I haven't been careful about the overall coupling or the overall normalization. So we're just going to look for something to understand how this thing can give something that's proportional to that result over there. So we need to express this in terms of spinors. We know how to express the momenta in terms of spinors. The thing that we don't know yet is how to express the polarization vectors in terms of spinors. And there we can use, again, many possible forms you could use, even for circular polarization. And in fact, many forms were used before the form that I'm going to write down was introduced. And this is a form that's due to a trio of researchers who were then at Tsinghua University. And in the West, it was called the Chinese magic. And the thing that's actually kind of interesting about it from a historical point of view, I mean, this happened before everyone except Ricardo and possibly Henrik were born, but this was really just a few years after the universities in China reopened when Mao's death brought an end to the Cultural Revolution. So I think from that point of view, it was also very, very interesting. So these are explicit forms for the polarization vectors. And we're going to use a new null vector Q. In fact, we really only need the spinor, the tilde spinor. And this thing is known as the reference momentum. And subject to certain constraints, it can be chosen freely. So the thing that's worth noting here, so this thing is going to go as minus 1/2, the helicity transformation, or the spinor weight. This thing is plus 1/2 in the numerator and plus 1/2 in the denominator, so it's actually invariant as we look at the weight with respect to Q, and that's the way it should be, because Q is supposed to be some arbitrary reference. And here we get a plus 1/2 in the denominator, which is the same as minus 1/2 in the numerator. So overall, this indeed does have the helicity of -1, corresponding to a negative helicity gluon. And there's a similar expression for the positive helicity gluon. Now here we do need the lambda spinner, but this Q does not have to be the same as that Q. It could be different. And here we have the angle bracket in the denominator. So we can check that if you take the two polarization vectors for the same momentum, that now we can use the Firth identity, and we would get 1/2 from the root 2's, 2 from the Firth identity, and then we have QI divided by bracket QI angle IQ, and that's -1, which is exactly what you expect for conventional polarization vectors for circular polarizations. So there are a few things that are worth observing, which I think it's pretty straightforward. So obviously we cannot choose a Q that would be collinear to I in either here for the lambda tilde spinner, here for the lambda spinner. But otherwise, we're pretty much free to choose any Q we want. We can choose the same Q for different different momenta, different legs, or you can choose different ones. And in particular, we could, in some cases, choose one of the other momenta as the reference vector for a given polarization. In the general case, when we're not looking at 3-point amplitudes, that's much more flexible. Here, we do have to be careful that for some of the 3-point amplitudes, all of the lambda tilde spinners are collinear. Yes? You can choose different reference momenta, and you can do that numerically or analytically, and you should always find the same answer for a gauge invariant quantity. So, and in particular, I didn't give that as an exercise, but I could, maybe I'll do that next time. If you change, let's say if you do the 4-point amplitude with Feynman diagrams and you use this this spinor helicity representation and you change Q, you should be able to verify that the result is then proportional to the momentum of that leg dotted into the rest of the amplitude. That is to say, it's an on-shell gauge transformation. Does that answer the question? Okay. So one of the things you can very easily see just from the identity is that if we have two different legs with both negative helicity gluons, and we choose the same reference momentum, then that will vanish. And that's, of course, also true for the positive helicity case. And if we have the dot product of a negative helicity gluon with a positive helicity one, and we choose the momentum of one of them to be the reference momentum from the other, then that object will also vanish. So so for example, in the minus plus helicity, then it would make sense to choose the same reference momentum for the two negative helicity gluons. But we cannot choose it to be the third. We cannot take advantage of this equation there because K3, the lambda tilde spinner for K3 is going to be collinear with the lambda tilde spinner for K1. So that's not a legitimate choice. But we could choose we can do the opposite thing, which is to choose, for example, K1 as the reference momentum over here. So we choose, for example, Q, Q, and K1 as the reference momenta for the 3 different gluons. And then you can see that 2 of the terms vanish, and we're left with just 1 term. So K2 minus K3 dot E1, in fact, just the first term. No, sorry, it's the second term. And we can use momentum conservation to write this as 2 times K2 dot E1 and then E2 dot E3. And we now plug it in and do the use the Fiertz identity. We're going to get something that's proportional to 1, 2. Sorry, this is not jumping one step ahead. It's proportional to 1, 2 Q divided by Q1. That's from the first factor. And then we have 2, 1, 3Q from the contraction of the 2 polarization vectors. So the 2Q and the 2Q will cancel here, but now we're left with Q1 and Q3, so we need to multiply this, the numerator and denominator, by something, and then use momentum conservation again. And when we do that, then again up to a sign, we're going to get 1, 2 cubed. That's from multiplying another factor, and over 3, 1. And then we have Q1, 1, 2. And 3Q here. So now we're going to use momentum conservation. So of course, that would say replace K1 with K2 plus K3. But if we have a 2 here, then we're going to have the spinor product of 2 with itself, which will vanish. And so when we do that, we're going to be left with Q3, 3, 2. These cancel, leaving a sign. And then that sign then gets absorbed in order to put this into canonical form. So this thing is going to be equal to 1, 2 cubed, angle 1, 2 cubed, divided by angle 2, 3, angle 3, 1. So you can see that if we express the conventional Feynman rule in terms of spinors, we get the same thing that we derived from first principles without ever writing down a Lagrangian. And at that point, I will stop and see if there are any other questions.